Okay, yeah.
So please.
Okay, thank you. And thank you for the invitation. So it's actually quite nice having them. Okay, so let me start. So today we'll be talking about joint work with Juan Pablo Aguilera and Andres Weimann. Okay, yeah. So I'll say start with some relatively simple observation, and then we will move to some more general kind of results. Okay, so let me first remind you about fast-growing hierarchies. Okay, so suppose we have a countable ordinal such that we have fixed system of fundamental sequences. Okay. Yeah, so basically everything works as usual. And then we could define this fast-growing functions, as you could see below in the slide. Okay, so basically the usual definition, so nothing interesting is happening here really. Okay, so now, okay, so in fact, so say beginning part of the talk could have been done using this usual fast-growing hierarchy, but for some reasons that would say more relevant later in the talk, so actually I will be working with so-called norm-based fast-growing hierarchies. Okay, so what are the norm-based fast-growing hierarchy, and also what are norm function on ordinal? So again, so it's very simple thing. So basically, we are assigning a natural number to each ordinal to each ordinal below a countable ordinal lambda capital. And then what we want from this norm function is that for any fixed value of norm, there are just finitely many ordinals of this norm. Okay, so those are norm functions. And okay, so for particular examples, if you will be looking into, will be the case of the ordinal epsilon 0 and the counter ordinal notation system for it. Okay, so yeah, so let's consider the following function. So it's okay, so norm of 0 is 0, and the norm of a counter normal form, yeah, so will be this number. Okay, so basically looking at the norms of ordinals, and we are looking at the coefficients. So essentially, norm is the maximum. So basically, if you just write down this counter normal form as a big term, then our norm will be simply the maximum of all coefficients, so that natural number coefficients that occur there. And we basically are not allowing here coefficient 0. So like base case is 1. Okay, yeah, or ordinal simply 0. Okay, so of course, this function is not a valid norm function for epsilon 0. However, it's a valid norm function for any ordinal below epsilon 0. So the problem, of course, is that unfortunately we have infinitely many ordinals with any particular given norm. If you are looking up to the epsilon 0. Okay. But okay, so but in the case, so in fact we will be using this construction for ordinals below epsilon 0 rather than for the ordinal epsilon 0 itself. Okay, so now let's talk about how we define fast-growing hierarchy without fundamental sequences, but purely in the term of norm function. Okay, so it's kind of simple. So if you okay, look at the standard definition, so it works like this. So basically, base case was that f0 of x plus x plus 1. So now is the norm-based version. Basically, the minimum possible value of f alpha of x is x plus 1. So this say reflects this case of alpha equal to 0. And then what we say is that we simply take maximum of values of beta to x of x, where beta is an ordinal whose norm is bounded by x, and whose value is less than alpha. Okay, so of course of course it's not does not precisely match say in general does not precisely match any particular fundamental sequence based fast-growing hierarchy. However, the point is that this functions so the two constructions they give functions of the same growth rate. So yeah, okay. So so in particular, one could show this kind of result that you could see below. So basically, if everything is Kalmar elementary, so yeah, so basically all relevant functions are Kalmar elementary. So there is a bunch of conditions we need. Yeah. So in this case, so basically, the connection is that there's a Kalmar elementary function such that norm-based fast-growing hierarchy is bounded by fundamental sequence. Base fast-growing hierarchy of G of x, where G was some just Kalmar elementary function, and vice versa. Yeah. So basically, yeah. So basically, so essentially, both constructions they take the same kind of growth rate. Yeah. Well, yeah. But in practice, so the reason, as I told, basically the reason why I will need to use this fast-growing hierarchy, it will occur a bit later in the talk. But okay, let's nonetheless. So let's move on this this thing. Yeah. Okay. And second thing, so actually. So now to make some simplifications, also they are not really that essential until you see later. So we really work with are the so-called binary fast-growing hierarchies, and this is essentially the same thing as usual fast-growing hierarchies, but we are iterating a function 2 times rather than x times, right? So basically. For fast-growing hierarchies, this clause would be f alpha iterated x times, but here you have just b alpha iterated 2 times. Okay, and so again we have this norm-based version of the same thing, and it works exactly in the same way as before. Yeah, and so basically, so again, so this is. Okay, the binary fast-growing hierarchies and usual fast-growing hierarchies, they're kind of catching the same growth rate. So it doesn't of course work for every ordinal, but so basically for like already reasonably large and closed ordinals, it does work. So for example, of course, a b epsilon 0 has the same growth rate as f epsilon 0, but of course, but they catch up much earlier. So for example, b omega to omega has the same growth rate as f omega to omega. Okay, so the binary fast-growing hierarchy. Okay, so what we now will do is we will think about this fast-growing hierarchy as representation systems for numbers. Namely, okay, so suppose we want to say notation system for numbers below b alpha of n. Then the point is that we represent them as follows. So namely, all numbers below n are valid representation of numbers. So basically, we represent the really small numbers by themselves, and then we represent all the larger numbers as the following terms. So basically, we are applying this b alpha k of b alpha k minus 1, so on b alpha 1 of n. So we can iterate duplication of b alpha. And here k is, okay, so basically here we allow this empty set of iterated applications, and so of course we will have simply number n. And so the sequence of ordinals will be descending. So alpha k is the smallest one, then so we have larger ordinals. And so the crucial condition is that this norm of each next ordinal is bounded by preceding part of the term. So norm of alpha I plus 1 is bounded by b alpha I, so on b alpha 1 of n. So in fact, basically, so the way how one could say get to this representation is something like this. So if you basically think about say how one computes the alpha of n, so basically you compute by this recursive calls essentially. And what these terms are, basically they're kind of this the terms that are occurring in this computation process essentially. And so this is basically the reason why they give you a representation for numbers. But okay, so let me prove this multi-site statement proves this multi-site. Okay, so basically, yeah, so the set of n alpha normal forms is a system of unique representations for numbers k below b alpha of n. So what this means is that right, so basically for any number below b alpha of n, there exists this n alpha normal form such that its value is this number, and vice versa for any normal form like this, its value below b alpha of n, and finally it's one-to-one correspondence. Yeah, so basically, yeah, so this is a system of unique representations. And okay, it's kind of easy to prove this. Namely, we prove this. The easy way to prove it by transfinite induction on alpha. In principle, transfinite induction here is not that necessary. You could prove the same fact without using any kind of transfinite induction by complete finitistic reasoning. But this transfinite induction proof is easier. So basically, first we consider kind of the case of basis induction. So what it means is that there are no betas so that alpha, such that normal beta is less than or equal to n. So basically, kind of basically when we define this b alpha of n, we are falling into this base case. Sorry, this should be b alpha, not f alpha. Okay, so then b alpha of n will be simply n plus 1, and basically the same. So our representation system are kind of very simple. So basically we have numbers below n and number n itself, and of course we give our representation system for numbers below n plus 1. This is kind of trivial. Okay, otherwise, so basically if there actually is such a beta, then b alpha of n will be this b beta of n. And so then what we are doing is we kind of have this two system of representation. From one hand, we have this representation of ordinal, so of numbers below b beta or b beta of n, so below b alpha of n, as this b beta of n beta normal form, right? So because this is we have the stop function b beta, and this is first thing, and second, we have kind of a representation system for numbers below b beta of n itself. So this internal thing. And then kind of what we're basically doing, we are composing these two representation systems. And this gives us, gives us exactly this n alpha normal forms. So when it's substituting, so basically when we have this b beta of n of beta normal forms, then basically we have this inside of our term, we have this b beta of n, and then we are representing this b beta of numbers.
So it is for this property that we designed this system b alpha rather than the standard, more standard f alpha, right? So that for f alpha, something would be more complicated in this.
Yes, it's slightly more complicated. Yeah, actually, I have this on slides. If you want, I could say go forward and show you what's going on. Where was? Okay. Yeah. So this is the slide. So basically, you see, so they kind of what we are with f alpha, we kind of getting this power.
Okay.
And but basically, they're kind of very similar, right? So this is but it's slightly more, slightly simpler for this binary case. But basically So we are continuing for just for simplicity. It's nothing essential. It's in this choice of binary case. Okay. Now it's okay. Okay. Yeah. You're here. Okay. Anyway, so basically we are proving this by transfinite induction. So now let's so now our next goal will be to extend this binary hierarchy to a functor between natural on the category of natural numbers and strictly increasing matrices in them. Okay, so we are doing. Okay, so we are doing this. So okay, consider some function, some scripting monotone function between two natural numbers, L and L, and then we define this coefficient shift function. So basically, what we are taking this ordinal whose norm is bounded by k, strictly bounded by k, and mapping them to this ordinal whose norm is strictly bounded by R. And then we are doing this. So basically, we are just looking. So basically, this Cantor normal form. So we have this bunch of natural numbers there, and what we simply doing is that we are simply shifting these natural numbers according to the function f. And of course, so because f was a strictly monotone function, so it will get a valid Cantor normal forms after this. Okay. So this is a coefficient shift function given by a strict monotone one between two natural numbers. Okay. Yeah. Okay. So now let's fix some function again, function f, and some ordinal below epsilon 0. And then we define this function b alpha of f. That of course is mapped from b alpha of L to b alpha of R. So because we want to extend this b alpha to a functor. And this is kind of naturally defined in terms of this representation system. So namely b alpha of f. So basically, our to remind you, so basically our simplest case of representation is simply a small natural number, right? So basically, if you have representation system for b alpha of L, then for all k smaller than L, basically k is a valid normal form. So we should map this kind of normal forms, and we simply map them according to f. And so, of course, interesting thing happens when we are mapping the more complicated terms. And so what we want to do is basically we replace L with K, and we are doing some kind of, so basically we are applying F for coefficient shift in alpha. However, we couldn't apply F itself, right? So because, so basically F is suitable only to do coefficient shift in alpha 1, because alpha 1 was this ordinal whose norm was bounded by L. And hence we could do coefficient shift in alpha 1. But then alpha 2 is bounded by this b alpha 1 of its norm of alpha 2 is bounded by b alpha 1 of L. And hence we couldn't do this coefficient shift using simply F. So that's what we're really doing is we are applying this function b alpha of F itself to this ordinals to make this coefficient shift. And the point is that so this, in fact, this definition is well defined. So basically, we could think about it like this. So we are defining values of this b alpha of f on particular natural number by induction on natural number. And basically, when we are referring, so basically we are using particular values of b alpha of f in this construction of coefficient shift. We are always using only values that are already defined. So so it's actually not that hard to show that. Yeah. So basically, if one inspects how it works, in reality, this is valid definition. So using only this the values of b alpha of f that we defined before in the process. Okay, yeah, and so right, and so basically what we prove.
Small correction: the k must be in R in condition 2, right?
Wait, second condition 2.
The k is in R, right?
It should be R. Yes, thank you. Right, yeah, it's a typo. Yes, thank you. Yeah, it should be R. Anyway, yeah. So yeah.
Yes.
But only
Okay,
that
yeah,
K,
so-
not in the indices.
No.
Mhm.
Okay, so now, so now, right. So the proposition that you prove is that for alpha less than epsilon 0, B alphas are well-defined functors on the category of natural numbers and strictly monotone maps between them. Yeah. Okay. Okay. So now let's apply this fact to get some ordinals. Right. So and what we are doing, so consider this chain. So basically, we have initial embedding of 0 into 1, initial embedding of 1 into 2, and so on. Right. So basically, this if I have simply identity functions. And now basically we are applying, and so we have this chain, and of course its co-limit is simply omega, right? So basically the union of this, essentially the co-limit of course is simply the union of the chain, so it's simply omega. And now what we are applying this function B alpha to this chain. Here we have natural numbers and map. Okay, so this is sample. And actually we are getting from this we are getting quite large ordinals already. Okay, so here is here I can pick a bunch of examples. Okay, so basically if you have just omega, we are not getting anything particularly interesting. We are getting omega squared. So already when we're going to B omega times 2, we are already getting epsilon omega. Then we're going to omega squared, we're getting phi omega of 0. Then we are going slightly above here, already getting gamma omega. And yeah, and so right, and of course, as one could expect from say seeing this just for example, so when we're really going up all the way up to epsilon 0, then we are getting Pakhomov ordinal. Okay, so yeah, so this is right. So basically, what we are seeing here is that there is kind of connection between this ordinal defined by collapsing functions and this outgoing hierarchy. Of course, this so basically the fact that there's some kind of connection is not particularly new. So it is definitely well known in ages. So there was this definitely was at least motivation for some works of Girard. I think also there's some more explicit constructions by Bourgogne, and yeah, so basically it was kind of known that basically outgoing hierarchy. So basically when we are kind of going to the transfinite outgoing hierarchy, in the sense we're getting something like collapsing function. But as you see, so I'll show you first in this talk. So basically now we have a really nice connection between this notions. So far, because it's at this point, of course, it's not yet clear because it's simply computation of ordinals. But not so. Okay, kind of now we kind of need dilators. Okay, so let me remind you what the dilators are. Okay, so a dilator G is an outer functor on the category of linear category LO, so of linear orders and strictly monotone maps. Such that the functor G preserves pullbacks and directed colimits. Okay, yeah, so dilators are prior dilators that preserve well founders. So yeah, in particular, it means that their restriction to category of orders is simply will be simply a function between from category of orders to itself. Yeah, right. So, but it also we also have explicit, much more explicit definition of what dilators are. Namely, we could define this notion of denotation system. And so basically, we have this set of denotations. This should have been D. Okay. Anyway, so basically, D is this denotation. So basically, we have this set of denotations C. We have assigned hierarchies. S from C to omega. So basically, S of C is the hierarchy of the term C, and yeah, and then basically the valid application of a term C are application to a sequence of elements of linear order that are given in an ascending order. Okay, right. So basically, apply denotation system D to some linear order A. So this valid elements of this linear order will be this kind of tuple. And then, right. So basically, then we have natural definition of how D acts on maps. So basically, we are pushing maps inside denotations. Okay, and so there is this Girard-Moffon theorem that paradilators are exactly the functors that are naturally isomorphic to denotation systems. Okay, this is dilators. Okay, so now, so in this talk, what will be relevant is a certain special class of dilators, namely so-called weakly finite dilators. Yeah, so so dilator is called weakly finite if it maps natural numbers to finite orders. And okay, so of course it's more or less immediately obvious that weakly finite dilators, so they correspond to functions from naturals to naturals, right? So because when we restrict weakly finite dilators to simply function from natural to natural, then yeah, so naturals to cardinalities of this order, then we'll get the function from naturals to naturals. Okay, so this is kind of this is something, but so there's also a second kind of connection, and so where it's the step where finally this norm function really coming into play, namely given some denotation system that is a weakly finite dilator, we could consider this ordinal D of omega. And the point is that the fact that D of omega was obtained by this dilator, in fact, gives us the norm function. This is actually quite natural one. Namely, the norm function will simply map an ordinal representation alpha to minimal n, such that alpha is an element of D of n. Right? So this is kind of very natural definition in the setting. And so, of course, given the fact that this dilator was weakly finite, there are only finitely many elements with a given norm. So because all dn's are finite, and the cardinality of dn is bound on the number of elements whose norm is bounded by n. Okay, so basically we have the important point here is that we kind of this weakly finite dilators, they kind of could be formed simultaneously two roles. So from one hand, there are something like fast-growing functions. Okay, not necessarily fast-growing, but we are mostly will be in the case of when they're functions. So there are functions from naturals to naturals, from one hand, and from other hand, there are this ordinal notation system with norm. Okay. So now what we are doing is we are
but not every norm defines norm function in the sense of your, let's say, beginning of your talk would define such weakly finite.
It's not true, no. Mm-hmm. Because wait a second. No, it's not true. So because I think that restrict basically if our norm function is given by weakly finite dilator. There's some restriction on the growth rate of the number of elements of particular norm. In particular, what couldn't really happen. Yeah. So what couldn't really happen is that somehow you have, say, a bunch of elements with some small norm, and then you have no elements with some larger norm. And I think it simply it's not possible with this Delator-based norm functions. And of course, it's possible if we simply have abstract functions, we could have such kind of gaps. So let me have simply no elements of particular.
Okay.
Yeah. Okay. So now what we will do is okay. So we are looking at the construction of this binary fast-growing hierarchy when our ordinal index is d of omega for some weakly finite Delator d. Right. So basically, then of course, again, so we're doing the same stuff we have seen before, right? So we have this system of representations for numbers below bd of omega of n. And then we could extend this this map from so basically using this representation system for numbers, then we could define how BD acts on functions. And so it's the same thing that we've seen before. So yeah, okay. And again, so the point is that this BD is well defined. Function from natural tensor, but however, in fact, it extends to a unique Delator. So this is probably not entirely trivial fact. So, right. So basically, we have this function from natural numbers to natural numbers. Then basically, you could take this direct limits. So basically, given any arbitrary order, we could say represent it as a directed co-limit of finite orders. And using the fact, we could extend, uniquely extend any function from natural to natural to directed to limit preserved function from linear orders to linear orders. So the uniqueness is nothing special about it. But of course, important point here is that so there are two important points. First, that we are getting this function that preserves pullbacks. And second, that we are getting a function that preserves all founders.
Okay. Preservation of pullbacks on infinite orders comes directly from preservation of pullbacks on finite arguments, right? So you would only need to check this on
right. So yes, of course, yes. Yeah, but in fact, in the setting, it says the preservation of pullbacks. We kind of will get it almost for free, so this is not really a big deal. Yeah. Okay, so yeah. Okay, so actually, so now, so to really better, okay, so in reality, to better investigate this function BD, it will be very useful to switch to a different definition. That will be more or less obviously correspond to say give us the same function up to natural isomorphism, but yeah. But also, so it will be easy to investigate it from one hand, and second, it will give us a very clear connection with ordinal collapsing functions. Okay, so yeah, so here I'll be using this notion of support of elements of the order of the form D of A. So basically, you have Delator D and order A, and you can see this order D of A. Then, so basically, so assuming that D was have the notation system, then its element of D of A will terms, and support of this term apply of the term is simply this argument of the term. Yeah, so it's kind of very natural. Yeah, so now let's define this, give new definition of the function BD. Yeah, so now given the linear order A, BD of A is the least by inclusion linear order such that, so first it contains the fixed isomorphic copy of A as its initial fragment. So basically, we start our order BD of A with an isomorphic copy of A. And then we add a bunch of formal collapsing expressions. So namely, we are taking this base 2 counternormal forms, where, or say, this ordinal from the top is this alpha i's. They're from D of BD of A, right? So basically, right. So this is kind of the set of these terms defined in terms of the order itself. And okay, so of course, then we have this natural condition for cardinal form. So that's basically alpha 1 is greater than so on, greater than alpha n. And this crucial condition that in fact corresponds to our inequality on norms that we've seen before is that support of alpha I, this should have been A I plus, it should have been alpha I plus 1. So support of alpha I plus 1 is bounded by the collapse of 2 to the alpha 1 plus so on plus 2 to the alpha n. And then comparison between collapses is the same as comparison between natural comparison between corresponding counternormal forms. Okay, so that of course there are a few questions. So basically, why this even works, and so what is the complexity of this definition? Okay, so the first point that is this is basically a positive inductive definition. So you and so basically we could kind of build this order BD of A in stages, right? So basically we start with the order A prime. Then we are looking at what kind of expressions we are getting in this item 2. And then, okay, so we have naturally extended by this order. So this will give us the order on the step 2. Then we are kind of applying the same construction, but now so here instead of using BD of A, we are using our order of the step 2. Then we are here using order of the step 3, and so on. And okay, important. Actually, if one inspects this definition, what really happens that it's it reaches a fixed point in simply omega many steps. So we don't really need to go to some transfinite ordinals. So basically, this simply stops. And this is basically because it's delayed. So any particular notation depends only on finitely many ordinals, and so basically using this factors when one investigates how this works. So one will see that basically this inductive definition will reach a fixed point in just omega many steps. So in fact, it's kind of efficient, and so we could talk about this construction in series like AC0 and in fact even RC0. Yeah. So this is so this is actually completely feasible definition. Okay. So now let's move to the main theorem. Okay, so yeah, so this again, so this is okay. So this is joint work with Juan Pablo Aguilera and Andreas Weimann, and of course, and in fact, all results that are not attributed to other people are due to us. This talk. So okay. Okay, so we have the so the following is equivalent of RC0 Pi-1-1 comprehension for any weakly finite dilated D. BD is a weakly finite dilator. And finally, that for any dilated D, BD is a dilator. So yeah, so what's the difference between items 2 and 3? So the difference is it's not that big. However, it's like, of course, item 3 is more general one, right? So because so yeah, what we are stating there is that right, so basically we could apply B not only to weakly finite dilators but to arbitrary dilators. Of course, with our initial definition in terms of this, Fedor hierarchy, this wouldn't work. However, this definition in terms of ordinal collapsing fashion really does not uses the fact that D was weakly finite. So this works for any orders. For any delays. Oh, sorry. Actually, I think I forgot to mention one important thing. Basically, why definition in terms of the collapsing functions and definition in terms of this denotation system for fast-growing functions are the same. No, but it's kind of triviality. So basically, we simply need to check that this restriction of this functor on arbitrary linear orders to the case of simply natural numbers will be naturally isomorphic to the functor just defined just to natural numbers, and it's kind of trivial if you really look at this definition. So, namely, of basically this isomorphic copy of A prime simply exactly corresponds to this numbers below L here. So what we get for 1, and for 2, basically, if you see that basically have this expression psi of 2 to the alpha 1 plus 1 plus 2 to the alpha n, and this exactly corresponds to this term, right? So b of here should be n because there was n before. Anyway, so basically we are simply say transforming this term, collapsing term into this term built of iterative application of b function. But this alphas are preserved, and in fact, this support condition exactly translates to this norm condition. And comparison, and then one could show that comparison of this kind of norm form exactly corresponds to comparison of terms. So this is exactly the same functors. Okay, so let's now move to this main theorem. Okay, so basically, main theorem, as I told you, so basically we have equivalent. We have this new equivalent of Pi-1-1 comprehension. That corresponds to this extensions of fast-growing. So essentially, so one other way to say this would be something like this. So if we say if some fast-growing function extends to the later, if some fast-growing function natural number extends to the later, then fast-growing hierarchy along this function applies to omega also extends to the later. Yeah, and this means to the equivalent of Pi-1-1 comprehension. Okay. Okay, so let's finally show this theorem that was even earlier, that basically that Pi-1-1 comprehension implies that B in fact maps the latest into the latest. And okay, this is kind of easy. Okay, so basically what we are doing is something like this. So we're considering this well-ordered part of BD of A. So you denote this well-ordered part as omega capital. And our goal will be to prove that omega capital is the same as BD of A. And then we are proving by transfinite induction on alphas from D of omega capital that basically we could, given this collapse from well-founded part, whenever we could append to it last term 2 to the alpha, then the result else is in well-founded part. And in fact, basically, if one really looks at how it works, it's kind of a really straightforward thing. So basically, so the point is that so basically, when we are looking at this ordinal with this 2 to the alpha, and so what are the ordinals below it? So basically, that's the Cantor normal form where we added to them something smaller. And for the smaller things, we already know that they're in well-founded parts. So this thing, so in fact, this holds. And now, basically, using this fact, it's really easy to prove that all elements, so basically, any element of this BD of A, in fact, is in well-founded part. So basically, it was this kind of sum. And then we basically proving by induction of I that basically the sum of first I argument is inside well-founded part. And in each, actually, we could justify each next step using the fact that we proved by transfinite induction. So this is kind of it. Okay. So yeah. Okay. So yeah. Right. So now we need to prove reversal. Yeah. So right now I'm proving that from item 3. So that for any delta d delta, it follows that Pi-1-1 comprehension holds. Okay. So yeah, and here we are using this result by Anton Freund. That so we have the following equivalent of Pi-1 comprehension, namely that for any delta d there exists a velour A such that this velour A will be what Anton has called Pakhomov fixed point. So this Pakhomov fixed point is this. So basically, it requires that there is this function theta that is a total collapsing function, and there's basically this condition for what does it mean for a function to be a total collapsing function. Okay, so in fact, this what I should comment here. That so basically, this this proof by Anton was like a really heavy work, technical work. So he really done this proof theoretic done this proof theoretic analysis to derive Pi-1-1 comprehension from the Pakhomov ordering principle. And here we will essentially employ this hard direction of his theorem to prove, the direction from the ordering principle to Pi-1 comprehension for our theorem. Yeah, and it's kind of very simple. Namely, we need to use this operator B to say construct this Pakhomov fixed point. And we are doing something like this. So basically, given delta D, we consider delta S. It will be delta omega plus A mapped to omega plus 1 D of A plus omega. Okay, there's some technical reasons why this should be exactly this delta, and actually I will not go here into this technical details. But the point is that as soon as we have choose F to be this kind of delta, and then we are considering this order B f of 0, then we have this total collapsing function, and it's kind of easy one. So namely, this total collapsing function is simply the function that maps alpha to the basically least well-formed collapsing term, such that last thing in this term is 2 to the 2 to omega plus 1 times alpha. Yeah, and so basically then there is some check. However, yeah, it's not even that complicated. So yeah, so by this within the conception, we kind of deriving this Pakhomov fixed point. Yeah, okay. So I think for this talk I will skip for this the fact that 2 implies 3. So this would be which would be the last thing needed to show that this 3 principles are equivalent. Again, so actually it's not hard, but I don't think it basically shows that much. So basically, there's a trick how you could say transform any delta into a weakly finite delta, then in a sense close enough to initial delta. Okay. Okay, so basically we already have seen this. So we have basically we could do the same thing for say more usual fast-growing hierarchy. Again, and so what really happened? So the real difference in the case of usual fast-growing hierarchy is that before we had single application of the same B alpha, but now we have iterated applications of F alphas, and then we have this kind of natural condition on this coefficient, on the number of times that we do the iteration. And then one could do the same kind of transformation from, say, function based on simply natural representation of natural numbers to this abstract form of collapsing function. Okay, so you could see it here.
So in item 2, it should be FD, right? And
oh, yeah, I think. Oh, right. Yeah, I think there's a bunch of typos. I'm sorry. Yeah, yeah, right. So there should be FD everywhere, right? So it's never BD. So now I'm talking about FD. Yeah, I'm sorry. Yeah. Okay. Yeah. Yeah. So basically, yeah. Right. So, and the point is that what changed is that now instead of so before we were talking about collapses of this base 2 counter-normal form. Now we are talking about collapses of base omega capital counter-normal forms. But yeah, and now this essentially what before this the number of times which we iterate the fast-growing functions, they are now becoming coefficients for this base omega capital counter-normal forms. Yeah, but otherwise kind of the same thing. So it's kind of similar. And again, so we are getting the same kind of general results, but there's really nothing new here. Okay. Okay. So finally, let me talk about some, I think, a curious observation that kind of simplifies some of existing theory around this kind of things. So namely, so there is this classical result of Girard that slow-growing hierarchies, they are much less powerful than fast-growing hierarchies. So to remind you, basically, slow-growing hierarchies define in terms of fundamental sequences defined as like this. So G0 of x is 0, and then when we go to the alpha plus 1 of x, we are simply adding 1. Okay, and this will be this slow-growing hierarchy, and then okay, actually, there's a slight problem with slow-growing hierarchies that actually they're quite sensitive to the choice of fundamental sequences, but for certain natural, but this theorem of Girard works for certain natural choices of fundamental sequences. Okay, so now let's see what happens when we go to this norm-based slow-growing hierarchies and how, in fact, all of these things completely trivializes. So because in fact the Girard result involves quite a lot of computations. But now we could do it kind of completely for free. So we are considering this norm-based slow-growing hierarchy that is defined exactly as usual slow-growing. So as our other switches from fundamental sequence to norm-based hierarchies. Right? So it's the same thing. So now basically we are be getting maximum of the g bit of x plus 1, where normal bit is bounded by x. And in fact, one thing how what the thing does for weakly finite dilators. So basically, our norm coming from a weakly finite dilator. Okay, so the point is that the alpha of x is simply compute the number of elements below alpha of a whose norm is bounded by x. And this means that, in fact, this slow-growing hierarchy, GD, the natural factorial extension of the slow-growing hierarchy, GD, is simply naturally isomorphic to the function D itself. So it's basically identity transformation of weakly finite dilators. And now let's consider the following. So basically, okay, this is so I don't give the details here, but so basically, okay, then we have this certain natural dilator such that its value on omega, so it actually should be weakly finite dilator. So we have this natural choice of weakly finite dilator such that its value on omega is epsilon 0. So in fact, it's not exactly Cantor-norm forms dilator, because as we've seen, this Cantor-norm forms dilator, it's really really kind of the construction breaking apart for Cantor-normal forms. So it works fine for all alphas below epsilon 0, but not for epsilon 0 itself. But basically here, D is certain variant of Bickley-Misher form notation. Okay, yeah, but I guess there's some details here, but anyway. So but basically, it kind of happens to be more appropriate for the functorial, for the dilatorial notation systems. And okay, and then one could compute that this order type of FD of omega is in fact Bachman-Howard ordinal, as expected. And right, and then we kind of trivially getting that foreground hierarchy along FD of omega is the same function as FD, right? So right, so basically f epsilon, hence basically f epsilon 0 corresponds to foreground hierarchy up to Pakhomov ordinal, and this kind of in this setting is really extremely natural and trivial result. Okay. Okay, so this is okay. It's the last slide. So thank you again.